Okay, it's my great pleasure to start the last day's session of what's been a very interesting workshop. This promises to be the same. We'll start with Pietro Caputo speaking on rapid mixing of Gibbs samplers. Over to you, Pietro.
Thank you very much. Thanks again for the kind invitation to be here. And I'm going to talk about some recent work we did with my student in Rome, Daniel Parisi, and then with some other collaborators, Antonio Blanca, Zongchen Chen, Alistair Sinclair, and Daniel Stefankovic and Eric Vigoda. As you will see, this is a rapidly growing topic that has received a lot of attention. The main theme is to get optimal mixing time bounds for dynamics, stochastic dynamics for spin systems. And as you know, there is a huge literature about this already spanning several decades now. And it is mostly concerned with the local dynamics, namely what is usually called the Glauber dynamics, where you update a single spin at a time. But here the main focus was to understand more general setup where you have arbitrary blocks that are updated. So it's a general Gibbs sampler where you update arbitrary blocks. Essentially, each block is given some probability to be chosen, and when you choose that block, you do a heat bath update on that block. So that was the idea, to try to understand general non-local dynamics. And in some sense, there is a regime where we can get fully optimal results about that. Along the way, we also discovered some new things that can be of interest for the local setup. So it turned out to be successful in the sense that you can get optimal results for general block updates and also discover some new things about the local classical setup. So let me just quickly go over the plan. I will look at spin systems on a generic graph, G, and we will look at a general class of Gibbs samplers, as I said, associated to arbitrary block updates. And then the key notion that I want to introduce here is something we developed with my student Daniel. It's the notion of general entropy factorization. And this entropy factorization notion immediately yields the mixing time bounds that we want. So basically, the main challenge is to establish the entropy factorization. And so I will try to tell you a few things on how to prove entropy factorization. And this will lead essentially to three setups, three different situations where we are able to prove entropy factorization. One is when you have a so-called strong spatial mixing. Another one is when you have spectral independence. And another one is when you have a good contractive coupling that controls one step of your Markov chain. But I will get to that in more detail later on. Here are a bunch of papers that can be looked at, that I will mostly refer to in the following. This is the paper where with Daniel we introduced the block factorization of the relative entropy, and these are subsequent papers where we apply this concept to several non-local dynamics, such as the Swendsen-Wang dynamics. And then there is this more recent paper we have where we collect several things together and improve considerably over the results we obtain. And there is also an interesting part about coupling that is completely new. And of course, I should say that some of these things are heavily based on some recent impressive work of Anari, Liu, and Oves Garan, who introduced the notion of spectral independence. Also on some work of Chen, Liu, and Vigoda, who were among the first to realize that this notion of spectral independence can be used not only to prove polynomial bounds, but actually optimal mixing bounds for local Glauber type dynamics. So let's go to the setup, and please interrupt me anytime, because I'm not sure I'm able to see the chat or the people who want to ask questions. So please stop me. Okay, so good. So the setup is familiar to most of you, I'm sure. So it's a spin system on a graph G. So that means it's a Gibbs measure. Let's say that we have a finite number of spins at every site. Let's say Q spins or Q colors, if you prefer. And at each site of the graph, you have one of such spins. The classical examples to keep in mind. So we want a Gibbs measure mu, and the classical examples to keep in mind are, say, the Potts model, where you count the number of edges that have the same color, and this is m sigma, and you take the probability measure, which is proportional to exponential of beta times m sigma. And when q is equal to 2, this is the Ising model. When beta is greater or equal 0, this is ferromagnetic situation. Then another popular model is the Q colorings, namely you just look at the uniform distribution mu over all proper Q colorings of G. So you assign colors in a way that there are no two neighboring vertices with the same color. Another important model is the hardcore gas, where you take probability measure which is proportional to lambda to the cardinality of an independent set. So its probability measure is on independent sets of G. That means that you take a subset of the vertices which has no edge of the graph. And so you take an activity parameter lambda, and lambda to the cardinality of your set is the independent, is the Gibbs measure corresponding to the independent sets, to the hardcore gas with parameter lambda. You have only two colors in this case, 0 or 1, and 1 tells you that your vertex is inside the set. So these are classical statistical physics model, and famous problem is to sample from these distributions, and you want efficient randomized algorithms that sample from this. So a classical family is obtained by choosing a region lambda in your set, in your graph, and updating the configuration on that region according to the conditional distribution of your Gibbs measure, given what you see outside of that lambda. So this is your conditional distribution, and you can write it in this compact form, mu lambda tau. Tau would be the boundary condition. Also, it's common to think of it as a pinning. You're just pinning down the spins outside of lambda. And this is the notation we will use for the function that maps omega to R, where you pick a boundary condition and you take the expected value of some given function f according to that boundary condition. So this is the usual Gibbs measure formalism. Now you define the general Gibbs sampler. You pick some weights alpha lambda. So for every set in your graph, for every lambda, you pick a weight alpha lambda. And you can assume it's a probability over all subsets. There's no loss of generality here. So the sum of all the alpha lambdas is 1, and they are all non-negative. And you consider the Markov chain, where at each step you pick a set lambda according to alpha lambda, and you replace the spins in that set according to the conditional distribution, mu lambda on sigma. So that's exactly the heat bath move we were talking about. And a way to write down the stochastic matrix associated to this stochastic operator of the Markov chain is to write P alpha applied to a function f as the mixture, as the convex combination of mu lambda f with the weights alpha lambda. You can call this as the alpha weighted block dynamics. Okay. Of course, a familiar example is when you pick alpha lambda to be a single site, uniformly chosen single site. This is the case where you just pick singletons. That's the Glauber dynamics. But it's completely general, the definition. And of course, you can also write the Dirichlet form, but let's not get into that. This defines, in any case, this defines a reversible Markov chain, and under irreducibility conditions, this will converge to the Gibbs measure mu that you want to sample.
Can I ask a question?
Sure.
So I was wondering about the computational complexity of doing this conditional expectation. Whether if you're taking a block which is too big, it's actually difficult to sample these spins.
Okay. Yes. That's true. But there are situations. I mean, and actually, something that is very much used in practice is, say, if you have a bipartite graph like ZD, and you are trying to sample a spin system in a region there, one thing that you could do is you could pick with probability half all the even sites, and with probability half all the odd sites. That would give you a very non-local object. But on the other hand, because of the interaction along the edges, everything factorizes in a simple way. So the big average that you had actually gets broken down into trivial single averages. So yeah, it depends on the setup, but there are actually practical situations where you have huge blocks and still a very convenient computational complexity. So this is an example we can think of it. The standard Glauber, of course, but also say this even odd dynamics if you have a bipartite graph, or general, whatever. At this stage is just a general setup. So what is the main quantitative analysis for convergence to equilibrium is as usual in these problems, natural ways to look at the mixing time in total variation. This gives this familiar definition. So you take the worst initial condition and you look at how many steps you need to get close to stationarity in total variation. But okay, here we are doing discrete time. There is actually no essential difference in our analysis to do discrete or continuous time. So choose whatever you prefer. But the way we are going to estimate the mixing time is by functional inequalities related to entropy. And so let me recall the main notation here. Entropy functional is the expected value of f log f under the measure mu when f has mean 1, and if f doesn't have mean 1, you just normalize log f over mu f. And a common notation that is very convenient is to do the same for the functional when you restrict to a region lambda, and so you have frozen the configuration outside of lambda. So this expression, in this expression, it is understood that the configuration outside of lambda has been frozen. And of course, this is nothing but the relative entropy when mu of f is equal to 1, and it's the relative entropy of the measure f mu with respect to mu. Now, the key to estimate mixing time from relative entropy is the well-known Pinsker inequality, and it is standard that if you are able to prove a contraction for the entropy when you apply one step of the chain here, so entropy of Pf is less equal than 1 minus delta entropy of F, then you can get a mixing time bound for your Markov chain with kernel P. And this is just going to be of order delta minus 1, where delta is the contraction parameter. And then you have a log of 1 over mu star, where mu star is the minimum value of your probability measure. And for a hardcore system, you can take the minimum value of the allowed probability of the allowed configurations, of course. And for those who are more familiar with continuous time, this is just in continuous time, this would be the same thing as the modified log-Sobolev inequality, which is a functional inequality essentially expressing this bound here. But in discrete time, it is more natural to look at the entropy contraction of one step of the chain. And note that this bound often can be written in the following form. For our system is typically log of 1 over mu star is going to be an order log n, where n is the number of vertices. And this will often give optimal mixing time bounds if you are able to prove an optimal bound on this contraction rate delta. So let me come to the key concept here that is going to be used to study the general block dynamics. This is what we call the block factorization of entropy. This holds with constant c if for all functions and for all weights, that's the key, for all weights, you have this inequality here. Gamma alpha is times the entropy of F is less equal than a constant times the sum over all lambdas, alpha lambda of the expected value of the entropy of F restricted to lambda. So let me try to explain this. First of all, gamma alpha is defined as the minimum rate, as the minimum probability that a vertex is picked in your update. So you do the minimum over x of all the sum of all the lambdas that contain x of your weight alpha lambda. And why is this a relevant notion? First of all, because it's a bit strange because it's for all weights, so it has to hold with the same constant c for all weights, but there is a constant here that takes care of the weights. So let's think of some special case. First, one thing that you want to check maybe is what happens when mu is a product measure. When mu is a product measure, then this notion holds with constant c equal 1 for any choice of the weights. And this is a consequence of Scherrer inequality for Shannon entropy. And one thing that you can observe is that this inequality here is expressing the cost of separating the different components in your system, in a sense. So suppose your alpha is such that you pick with probability a half a region A and with probability a half the region A complement. So you're trying to break your system into two, A and A complement. And if the measure is product, then standard subadditivity of entropy tells you that there is no cost in breaking the system in two. You can estimate the total entropy with an upper bound of the sum of the two local entropies. But if the system is not a product, then there is a cost. And this constant c is precisely telling you what that cost is. But the point of this block factorization is that it's saying that there should be a cost c, which is the maximal for whatever partitioning of the graph you're trying to do. And even more generally, there can be overlap between all the sets that you're trying to decompose your system into. So it's a completely general bound that should take care of the worst case factorization that you have.
Excuse me, Pietro, may I ask a question?
Sure.
So, hi, it's Thierry Bodino.
Hi, Thierry.
Just the lambda or your decomposition of V is given as just the alpha lambda you're moving.
Yes, but lambda is arbitrary. You can take all of the subsets, and the alpha is a weight on all the subsets. So it's a probability on all subsets. And the point of the inequality is that this inequality should hold with the same C for all choices of the alphas.
But on all subsets.
Yes, but it can be, you know, another example is alpha equal to a uniformly chosen single site.
Mm-hmm.
So this case here. In this case, this inequality becomes the familiar factorization or tensorization inequality, which is written in this way.
Okay, but in this case, the subsets are only the sites, and you
exactly. Okay, but the point is that I want to say that block factorization holds if this inequality holds no matter how you pick the weights. So in particular for the single sites, but I wanted to hold for all choices of the weight.
Okay, thank you. Sorry for interrupting.
No. Any other question?
None at the moment. Please go ahead, Pietro.
Okay, thank you. So yeah, in a more familiar case where you just pick single sites, you have what we sometimes call the approximate tensorization. And this approximate tensorization is equivalent in our setting to the famous log-Sobolev inequality for Glauber dynamics. And in particular, there is a long series of famous works in the 90s saying that if your spin system, say in ZD, has strong spatial mixing, namely some exponential decay of correlation, then you have this single site factorization or approximate tensorization. And okay, you can do the same thing on a general graph. It's a little more difficult. The picture is not as simple, but you can certainly prove that if your interaction is small enough, then you have this single site factorization. This was done in several papers by myself with Mentz and Tetali, by Marton, then by Roland and Thierry. Then there were some nice developments for log concave measures by Krayangu and Musa, Herman and Sales. And even very, very recently, there were some major progress made by Anari and his collaborators and by Chen and Eldan using their stochastic localization framework. So basically the message is that if you want an approximate tensorization, namely factorization of single sites, then there is very, very strong theory now that has been developed and it's quite optimal actually. So you can prove this kind of estimates in the regime you want. But for the general weights, there was no theory in general. And so we tried to develop that. Let me just tell you very quickly why the block factorization statement will imply an interesting mixing time bound. First of all, this is simple. This is just convexity. So let me just give you quickly this slide here. So if you have the block factorization with constant C, then all of the block dynamics, so namely for all weights alpha, you have a contraction, and you have a contraction with the parameter delta, which is exactly the gamma alpha over C, where gamma alpha is the minimum probability to be picked for a single site. And so by the argument with the Pinsker inequality, you get a mixing time bound, which is 1 over gamma alpha times log n. And this is for any choice of weights, provided you have the block factorization. Okay, I'm not going to prove this, but it's very simple convexity. So this is essentially why we are looking at the general block factorization. Okay, and often in all cases of interest that I'm aware of, this bound really gives the optimal mixing bound up to constant. So you don't lose anything more than a constant here, which is kind of impressive because you're really using arbitrary block. Okay, so now I guess I have only maybe 5 minutes, I don't know, but the work starts here because you want to prove block factorization. So you want to say, when am I able to prove block factorization and therefore infer all these nice mixing time bounds? And so there are basically 3 situations we analyzed. We started with my students in this situation, which is more kind of a standard setup, because as we said, this is a setup where the single site factorization was very well known from the 90s. And it's the setup of ZD spin systems with strong spatial mixing. And we understood that in this setup, you can prove the full block factorization statement. So we were quite happy with that. It turned out that actually you could also extend this optimal bounds to more general, to other non-local dynamics, such as the Swendsen-Wang dynamics. And that was a nice surprise. But then we understood that actually you can prove this block factorization as soon as you have spectral independence, which is a powerful notion that was introduced recently by Anari and collaborators. And it's also a notion of exponential, of decay of correlation, say. And that will also imply the block factorization. And then we also discovered that actually, if you want to prove it, you could also use some coupling ideas. So, so you could use some coupling ideas to first establish the spectral independence, and then the spectral independence will imply the block factorization. So these are essentially the three items that were addressed in our work. So we started with the statement that in ZD, strong spatial mixing implies the general block factorization. And this required a complete revision of the classical recursive techniques that were used for single sites, because there is a main difference here. If you think of separating your system into two large blocks, you cannot do the single site recursive analysis that was done in the famous works of Struck and Zegarlinsky or Martinelli, Olivieri, and so on. You cannot repeat that kind of analysis. You have to do something that does not go one side by one side. You have to do something more global. And so we had to combine several recursive analyses to do this. But yes, so that was the first work we did with Daniel. And this gives essentially this result, that under SSM, the general block factorization holds with a constant C independent of n and the boundary condition. So everything is uniform, at least for spin systems on ZD. And the key observation is that it is actually possible to reduce to proving a bipartite factorization. Namely, the first case you want to try is to try to break your system into two parts, like the even and the odd, say. And this corresponds to taking weights alpha on the even equal alpha on the odd. And this requires a new recursive strategy because, as I said, you cannot use the usual approach, but then you can prove that. And another thing that you discover is that if you try to apply these same ideas to the Swendsen-Wang dynamics, then you can prove a factorization now, not in the space of spins, but you have to consider both the spin and the edge in the so-called Edwards so-called coupling. And what you can prove is a factorization of a preliminary factorization of your measure into spins and edge. So you can factorize the entropy into a spin entropy and an edge entropy. And once you do that, then you are back to something more similar to the first theorem, where you can prove the factorization for each of these two measures, essentially. So these were the results that, in particular, it allows you to go, say, up to the critical point for the ferromagnetic Potts model, for the ferromagnetic Ising model. Actually, Potts, even in dimension 2, you can go up to the critical point for the whole uniqueness region and get an optimal log n mixing time bound for the Swendsen-Wang dynamics. Okay, so I guess I don't have much other time, but the main message is that basically you can prove block factorization under these situations. And let me just add one word about this because it's kind of interesting. It's quite new, the fact that you're able to connect a purely coupling statement into a functional analysis, into a functional inequality statement. This is kind of unusual in our business because usually coupling proofs are quite separated from functional analytic proofs. But here, what you can do is show that a coupling will imply a suitable version of the spectral independence, and that will be sufficient to prove a full block factorization statement here. So this goes into the direction of establishing a relation between positive curvature and factorization of entropy, which is interesting in its own right. So I guess my time is over, so I'm happy to get any question if you have.
Let's thank you. Are there any questions?
Hi, Ben. Thanks for the nice talk. I have two questions, very short. The first one is, can you say also that this constant C equal to 1 for the product measure is optimal in a sense? So it will always be greater than 1. And also, whether any of these implications will also be stated, for instance, for non-Gibbs measures.
So the first question is simple. C equal 1 is certainly optimal because you can just restrict to a function of a single spin, and you would saturate the inequality, say. So C equal 1, C must be at least 1, yes. And the product case is really optimal in the sense that it has C equal 1, but also it's interesting that if you have a suitable negative dependence notion in your measure, you get again C equal 1, or at least there are examples where we can prove that C equal 1 is attained also for suitable log concave measures. So that's the first question. The second question, I'm not sure what you mean. Do you mean non-local interactions, or do you mean?
You cannot write them as exponentials of Hamiltonians.
Yeah, I mean,
but still on a spin space.
Okay. Well, in principle, I think the notion, of course, you can define it in any situation, but I'm not sure what to expect in. I mean, first of all, if the spin system has a very strong correlation, you don't expect any factorization to take place, because of course you can cook up examples like low temperature Ising models where you have where the minimum constant that C that you require there must be some exponential of n or something. So yeah, it depends on. I don't expect block factorization to happen all the time, only under suitable weak dependence conditions.
So I had a question, which also there's one in the chat, so it's kind of related. So Jean-Dominique has to say that what if you have non-reversible dynamics? And I will just maybe add to that, because one knows that in some case, non-reversible dynamics can mix faster than reversible dynamics. So in some sense, how would this be able to adapt it to that? And then maybe because we're short, so I just wanted to say also in the low temperature regime, as you mentioned, you don't expect block factorization, but I know there's been work now, but look, these are all mixing times. So you're looking at sort of worst case initial conditions.
Yes.
But is any of this adaptable if you choose suitable initial conditions and then try to look in the low temperature regime? So yeah.
Okay, thank you. Okay, so the first question is about non-reversible, I guess. Well, of course, the relation between entropy contraction and mixing time is general. It doesn't have to do with reversibility. So that you can try to apply in any case. So you can still try to prove entropy contraction estimates. The problem is that if you have block factorization, the notion I introduced here, this will not give you the contraction for some non-reversible process, because this is really tailored for heat bath dynamics, which is reversible the way I've defined it. So I guess you would have to modify your notion of factorization in order to get some useful information for some non-reversible process. Of course, the speeding up is a very interesting matter, and I don't think this technique I'm using here will have much to say for that, though. On the other hand, for low temperature, there's several things that can be said. Maybe, for instance, our result for Swendsen-Wang by a duality gives you an interesting result for low temperature in 2 dimensions. Also, you can do some other things for low temperature Ising model, but yeah, the question of choosing the initial condition, which you were saying, Kavita, is a delicate one. I guess that these functional inequalities are not very robust. I mean, the kind of notion we are using is too strong to attack that kind of problem. So one would have to look at modified versions that go in that direction. So yeah, I don't think.
Thank you so much. Thank you so much, Pietro. There are a lot of questions we want to ask. Too bad you're not here, but thank you so much for taking the time and for a talk. So let's thank him again.
Thank you all for
Thank you.